There's a reference in chapter 2 of the Manovich book, this week's recommended reading, about a life, about artificial life. And the classic example of this dates back as far as 1970, what is this, 50 years ago now, to mathematician John Horton Conway's Game of Life, which is very similar, what we call cellular automata. The screen is made up of lots of tiny little squares here, easy to see how we do that in processing. And we have rules that are applied to each square, each cell of the screen in turn. And the rules are very simple. Any live cell with fewer than 2 live neighbours dies. Live cell with 2 or 3 neighbours lives on to the next generation. Any live cell with 3 live neighbours dies. More than 3 live neighbours dies by overpopulation. And dead cells with exactly 3 live neighbours become a live cell. And you can see in the little GIF here what happens if we run that iteratively, repeatedly on the cells of the board here. So that's what we're going to aim to do in processing now. So we're going to start by setting up the board, and the board is going to be a key idea to this. So rather than working directly with the screen, I want to keep track of what's happening in each cell of our Game of Life board, and then later on we're going to display the state of the board on the screen. So we're not working directly with the screen for most of this. We're going to work with some abstraction of that, some representation of that, the board. We're going to start by drawing the screen, so set up the screen initially using our sort of void setup routines, and then we're going to have the sort of repeating drawing loop. So inside that, what we're going to need to do is compute the next board at each stage. So I'm just setting up here some comments in advance as to what my code is going to do. You'll notice the double slash at the beginning there to show that I'm doing commenting. Once we've got that, then we can... Computing the next is going to be made up of a number of different components here. So we've got to count the number of neighbours for each cell. I'm going to apply the rules of life to all of the cells, to each cell, to find out whether it's going to be alive or dead on the next generation. And then finally I'm going to want to draw the board on the screen. So I think that gives me an overall structure for my program there. Let's start then, as we mean to go on. Let's set up the board here. So some of this I'm going to abstract out as functions within my main sort of drawing the screen loop. We'll get to that in a little while's time. So we're going to have the size of each cell, so we could call that size, I guess. Let's see, that's not a protected word, and we're going to make that big chunky 8 pixels to be going on with. From that I can establish the number of columns, the number of rows in my board. So I have the number of columns is going to be equal to whatever my screen width is. I'm going to go with 600 for now, divided by the size of each of those pixels, and similarly the number of rows is going to be the height of the screen. Again, I'm going to go with 600 divided by the size of each of the squares there. Now here comes the key idea to this implementation of life. I want a 2D array saying the status of each cell. And processing allows us to do that. These are individual single variables, named locations in memory. What I want to have here is a grid of those. So I've got rows and columns worth. And our convention for that is these square brackets to show where we are. This is a 2-dimensional array, and that's going to be equal to a new set array of integers, which is determined by the number of columns. That's going to be, I don't know, is that 75 or something, by 75 rows. And we'll come back to that very, very soon. Okay, so I now need to, so that's declared this array, the board, and initialize that as, it's declared an array, the board, which is made up of however many columns, however many rows of integers. So imagine a 75 by 75 grid of memory locations. So we've got to put something into those memory locations. I'm going to do that inside a couple of for loops here. So we're going to go down each row of the screen. So for each row of the screen, or each row of the board I should say, y equals 0. whilst y is less than the number of rows, and keep increasing y. Then we do for each of the rows within that. Actually, let's just separate that out. That looks a little bit clearer. That's better. And then we're going to do each column within those rows, and I'm going to use x to iterate over those. For x equals 0, x is less than the number of columns. Whilst x is less than the number of columns, keep increasing x. And then what are we going to do? We're going to say for each of the memory locations on the board, so board x for across and y for down is going to be equal to, well, we could initialize all of these as empty, but I'm just going to take these as random numbers less than 2. And I want to make those whole numbers. So this is a whole number in the range, sorry, this starts as a decimal number, a real number in the range 0 up to but not including 2. If I just take the whole number part of that, the integer part of that, because remember my board array here is just storing integers, then I should end up with 0 or 1 in each cell of the board. Okay, there's my semicolon going in. Close the loop for the columns, close the loop again for the rows, and close that whole collection of code there. So that should set up my board very nicely. We're now going to do the void setup stuff for the screen, which is relatively straightforward on this occasion. So we're going to have here void setup, and we're going to do this as size 600 by 600, and we're going to have a frame rate of, let's go with 24 frames per second, which might be optimistic, but no, at 8 pixels wide that should be absolutely fine. I think that's all I'm going to do in setup for now. Most of the interesting stuff goes on inside this drawing loop, so let's get on with that now. Okay, so drawing the screen, the key idea, so this is inside void draw, and what we're going to do here is just each time we go around the screen reinitialize this as a black background. You can change the color later yourself. And then I've got to compute the next board. Okay, and that's where the interesting stuff is going to happen. And the trick for this is we're going to create a new array. Just as we have the board as it's in its current state, I want to work out the next state of the board at each move in this game of life here. So that's exactly the same format as we've got here. In fact, I can copy this down to save having to do lots more typing. But rather than the old board, or the board that we've already got, I'm going to actually create the next board at this point to be exactly the same as, I'm declaring that as an array with the same number of rows and columns in it. Okay, so then we're going to go off and count the number of neighbours for each cell here. And the best way I think of doing that is to separate that out into a function. So we're going to count the number of neighbours, and I'm going to do that as a function. So the number of neighbours for, oh yeah, we're going to do this by going around a loop, aren't we? So we're going to do each cell in turn. So just as we had here, iterating across all of these individual cells, we're going to do the same thing here. But this time, rather than putting a random number in there, I want to work out how many neighbours there are, and work out and then assign the value for the status of each cell according to the number of neighbours that we've got there. So count the number of neighbours. So we're going to, in here, count the number of neighbours for each cell. So forget about that for now. We're going to be working on the next version of the board. And so what we have going on here is the number of neighbours for a cell is going to be a whole number. So declare the variable and that's going to be equal to, let's call it a function here, count the number of neighbours for cell X, Y, which is where we are on the board at the moment. So we're going down each row and going across each column, counting the number of neighbours. This won't work because I've not explained what this function means, but we'll do that in a moment. Okay. Once we've counted the number of neighbours for each cell, then simply say that the status of the cell, 0 if it's dead, 1 if it's alive, is equal to, so status of cell X, Y, the current cell that we're working on, is what you get if you apply the rule of life to the status of the current cell, which is stored in board, given a particular number of neighbours that we've just counted. Okay, I think that's certainly one way of doing it. There may well be better ways of doing it. We've closed the X loop and we've closed the Y loop in that code that we copied there. Okay, so I'm going to come back to this. There is more code to go in here, but let's go and deal with both of those functions now. So counting the number of neighbours for a cell. This is a function here. So this is a new programming construct which allows us to bring out some of the functionality into a separate formula, if you want, a function that we can apply. So what have we got going on here? Well, this is going to return an integer. So the integer value, count neighbours, and we're going to pass this two parameters. The two parameters that we're going to pass it are both integers, the X position and the Y position of where we are on there. And then we run code when we give it those two values. Okay, so we're going to start off by saying there are no neighbours to the cell and then count each one that we find. So within this definition of count neighbours, I've got a new variable which I'm also calling neighbours, and I start with that as equal to 0. What I want to do for counting neighbours is go through the 3x3 grid around each cell and see whether there is anything in that square or not. So what we've got to do here is another bit of iteration. So let's go and do for, and we're going to use I for each row of that grid and j for each column of that grid. For int I is start off 1 to the left, so sorry, 1 above, I is -1, whilst I is less than or equal to +1, I 1 below, and keep increasing I on each pass around the loop. So that's doing each of the rows of this 3x3 grid around the cell. And then we're going to do the same thing here for the columns, which we're going to use j for. So we start with it equal to -1 whilst it's less than or equal to 1, so until we get 1 to the right, and keep increasing that by 1 each time. Okay, then what we do, the number of neighbours, which remember is just local to this function here, is going to be equal to whatever neighbours is at the moment, plus whether there's a 1 in that board or not. So we just add on the status or the content of the present cell of that board. So it's not x plus, it's not x, it's x plus I, sorry, x plus j for the column, and then y plus I for the row that we're in, x plus j, y plus I, adding that onto neighbours. That should be okay. Close that loop for the rows, and columns, and close that loop for the row that we're on. Okay, now you'll notice that we've gone through the whole of the 3x3 grid, which isn't quite counting the number of neighbours. We've got to subtract whatever the status is of the cell in the middle there. So the number of neighbours isn't quite as simple as that. We've got to take away the content of that middle cell of our 3x3 grid, which is simply board X, board Y. Now we've worked out the number of neighbours, we pass that back to the main bit of our draw loop, which called this function in the first place. So we return here the number of neighbours for that cell. And let's close the loop there. Okay, that should be a good definition. for our count neighbours function. So this line of code now should work. What we've got to do now is apply the rule of life, which is the thing from Wikipedia, to the status of that particular, to each particular cell to work out the status of the cell on the next iteration. Okay, so this is another function, whereas I've got my apply rule of life bit here in my helpful hints for what we're going to do here. So integer value rule of life for the current status of the cell. Is that 0, is that 1, is the cell alive or dead at the moment, with a particular number of neighbours in there. And that's going to, as I say, return an integer. Okay, this is essentially a fourfold if statement, I believe. Let's go back to our Wikipedia and just remind ourselves of what the rules are. And we have this thing going on here. Any living cell with fewer than 2 live neighbours dies. A live cell with 2 or 3 live neighbours lives. A live cell with more than 3 neighbours dies. Okay, so this is the status quo. Dead cells that are dead already will, so I'm going to do these in a slightly different order. Dead cell with exactly 3 live neighbours becomes a live cell as if by reproduction. So let's just have a go at seeing how we get on with this. So let's do, if the cell is currently alive, let's pop this in brackets. Okay, if the cell is currently alive and our code in processing, and indeed all Java and C-like languages, is a double ampersand for that, and the neighbours is greater than 3, then the cell dies on the next iteration. So if it's alive but there's lots of neighbours, then it dies off the next time round. So we return 0 from our function there. And I'm going to explain that that's by overpopulation. Okay, now we've got to do another test. All right, so for this I'm going to use this else if construction. So else if the status, if it's currently alive and the number of neighbours is less than 2, then we return 0. It's going to die on the next iteration, and that's because of underpopulation. Okay, else if it's dead at the moment, but if it has exactly 3 neighbours, let's just remind ourselves of the rule there. Any dead cell with exactly 3 neighbours becomes a live cell. Okay, so this is the generation of new life. So if the status at the moment is 0 and the number of neighbours is exactly 3, then return 1 at the moment, and that's by reproduction. And finally, otherwise it just stays as it is. Dead cells stay dead. Live cells which don't fit any of those criteria, in other words, in the range 2 to 3, the current number of neighbours stay as live cells. So my final bit here is else return the current status of the cell. And that's just as things are. Okay, and that should give us an iterative rule of life there. So just checking that everything looks as though it looks correct. So that's worked out the new state of each cell on the board. Once we've done all of that, then the next bit is really very easy, because all we have to say is the board itself simply becomes the same as that next state that we've just calculated, and then we can call another function here which draws the board itself. And that's the end of our drawing the screen loop, I think. Okay, let's go out and draw the board on the screen. So drawing the board on the screen, we've got to go through each of these rows in turn here. So let's copy our boilerplate code for that, and we're going to do something for each of those cells. So draw the board on the screen. What did I call this? Draw board. And this is a void instruction because it's not returning a value, it's acting in the world here. So void draw board, and that's going to be for each of these cells in turn. For y, for x, then forget about all of that because we've done that bit already. But what we're going to do here is plot a point on the screen. So for each of these cells in turn, we are going to plot a rectangle, I think. Yeah. So yeah, it depends on the status of the cell. So it's as simple as that, isn't it? If the board at that cell xy is equal to 1, in other words, if it's alive, then we're going to set a fill up as bright. Otherwise, we're going to set the fill as quite dull. Let's go for 64. Probably. Right, that's 25% grey. Oh, missed a semicolon. Semicolon there. Close the square bracket. So that's set the colour up. We now actually have to draw the rectangle. And the rectangle is which row we are on, sorry, which column we're in, times the size of each cell. The column we're in times the size of each cell, and then the width of the cell and the height of the cell. Close that for the rows, close the loop for the columns, and return from the function call. Okay, no error messages coming up. I think we have this now. Okay, what's going on here? I've got a couple of curly brackets which seem to have just been left in. I'm not quite sure where they came from. Could have been copying and pasting. It was copying and pasting stuff earlier, wasn't it? Because I closed those loops twice. Good. Okay, fingers crossed here, folks. Let's see how many error messages we get. Okay, for int. Oh yes, and the convention is semicolons, not commas. I'm sure you would have spotted that as I was typing it in the first place. Right, let's run that. Okay, int rule of life status. Okay, unexpected colon. Oh yes, we have to say what these variables are within the loop. So they're both integers. Okay. And it doesn't work. Oh, hold on. Bouncing ball. I've got an array index out of bounds exception -1, so that's not looking so good. Okay, we're going to have to close that by hand, force quitting that bit of the loop. Okay, so that didn't go so well, did it? I've got to figure out what exactly the problem is with that. It's something in here by the looks of it. It's where, so it was when we were counting neighbours is equal to the board. Okay. I know what the problem is. We're looking in the wrong place here. So yes, when we're computing the next, we don't actually look at the edges of the board. So I'm going to start with one row down from the top and one row in from the side. I am going to do the last column. Last row, and I'm not going to do the last column. So let's try that now. That's got it! Okay, so a few bugs there in the code, but I hope you enjoyed the experience of me panicking as I had to try and fix those. And I just can watch this for hours, I really can. You see these little gliders sort of flying across the screen there, and then it enters something approaching a steady state. So that's life, as they say. We can, of course, change the size of each of these cells. So let's take this down to like just 2 pixels per cell, and it will slow down dramatically when we do that. Oh, it's not too awful. It's too small to actually see there, isn't it? I'm trying to spot the gliders, the ones that are moving across the screen. Okay, I think that's significantly less than 24 frames a second because, it's having to calculate 300 by 300. What is that? That's a huge number, isn't it? 90,000 cells in a matrix in an array at each step of the loop there. There's one more thing I'm going to do before I stop the recording, which is to create another event about interacting with this. We're meant to be talking about interfaces this week. So let's create something which happens when we click on the mouse. So I'm going to pop in another bit of code here when the mouse is pressed. So void mouse pressed. And then we're going to get the status figure out what the status of each of the cell where the mouse is pressed is. So I want cell X is int cell X is equal to the mouse pointer location X divided by the size of each cell. Okay, I'm not sure about that. Okay, it's a system variable, and the Y location is equal to mouse Y divided by the size of each cell at the moment. Then what we're going to do is change the status of that cell. So when we click on something, if the cell is dead, it becomes alive. If the cell is alive, it becomes dead. So I'm going to just change the board directly. The board at cell X, cell Y becomes equal to 1 minus the status of the board as things stand. That should work. Okay. It's complaining about these. Oh yes, it's the wrong array notation, isn't it? And made the same mistake there. Okay, that looks better. And that grid was really far too small. Let's go for something in the middle. 4 pixels per cell. There we go. That's nice, isn't it? Okay, and I should now be able to interfere with some of these. There we go. Let's put an extra cell in there and kill those off. Oh, got something running. That's made a stable state. Oh, that's pretty pattern. So yeah, I'm just killing cells or making cells alive that were dead previously as I click on the mouse. Okay, I think that's good. That's quite long enough for you to have watched one of these videos, so I'm going to stop this now.